Today I'm going to solve the previous year GATE problems from the chapter Radiation. The first question is a hemispherical furnace of 1 meter radius is 1 meter, inner surface emissivity is epsilon is equal to 1 of its roof, temperature is 800 Kelvin, floor's emissivity is 0.5 and it is kept at 600 Kelvin. Stephen Boltzmann's constant is given as this, use this value only. The net radiative heat transfer in kilowatt. Okay, be careful to mention the answer in kilowatt, so write at the top of your notepad that you have to write the answer in kilowatt. From the roof to the floor is okay. Hemispherical cavity, let's draw a rough hemisphere. This surface, let this be 1 and let this surface be, this flat surface be 2. Okay, net radiative heat transfer from the roof to the floor. Okay, what we know is if we can draw the total radiation network of the heat transfer flowing from 1 to 2, then there will be one surface resistance of the surface 1, then we will encounter a space resistance, then again we will encounter a surface resistance of this surface 2. So we know that the surface resistance is equal to 1 minus epsilon upon A epsilon, whereas the space resistance is F12. Okay, so can I say that Q net from 1 to 2 is equal to sigma T1 raised to the power 4 minus T2 raised to the power 4 upon 1 minus epsilon 1 upon A1 epsilon 1 plus 1 upon A1 F2 plus 1 minus epsilon 2 upon A2 epsilon 2. Okay, T1, what is T1? T1 is 800 Kelvin. We have been given this. T2 is 600 Kelvin. This is also been given. Sigma is also given. Epsilon 1 is 1. So this becomes 0. Epsilon 2 is 0.5. A2 is, yeah, it is given because the radius has been given, and epsilon 2 is also given. A1 is we know A1. Okay, what we don't know is F12. Okay, so whenever you have to find F11, F12, okay, you know what is F12. F12 is fraction of radiation energy going from 1 to 2. Okay, so whenever you encounter this type of problem where you have to find F12, F21, F11, F22, whatever, we know that we have two rules. One is the summation rule. That is F11 plus F12 is equal to 1, or F21 plus F22 is equal to 1. And there is one more rule, that is reciprocity theorem. That says A1 F12 is equal to A2 F21. Okay, so A1 F12 is also equal to A2 F21. Okay, and we also don't know F21. So what we do is we apply this summation rule. F21 plus F22 is equal to 1. Can I say that F22 is 0? I can say, because this is a flat surface. The fraction of radiation going from 2 and falling on 2 is 0. So this will be 0. That implies F21 is equal to 1. Now replacing A1 F12 with A2 F21, F21 becomes 1, so this whole term becomes A2. All you have to do is now put the values and get the answer. I'll tell you the answer. The answer is, you will get in watts, 24929.166 watt, and convert it in kilowatts because you have to fill the answer in kilowatts. So that will be 24.929 kilowatt. Okay, this will be the answer. And also, you know, the areas, I mean, that will be A2 will be pi r square, whereas A1 will be 2 pi r square, surface area of hemisphere. Okay, let's move on to the next question. A solid sphere of radius r1, 20 mm, is placed concentrically inside a hollow sphere of radius r2, which is equal to 30 mm as shown in the figure. The view factor f21 for radiation heat transfer is, okay, as I've told you earlier, view factor f21 you have to find. Always remember those two rules: summation rule, summation rule, and the reciprocity theorem. Okay, reciprocity theorem. Whenever you encounter these type of problems, okay. So this is surface 1, it has been given, and this is surface 2. Okay, so can I say by summation rule that f11 plus f12 is equal to 1? And can I say that f12, that is fraction of radiation energy from 1 on 2, is 1, is equal to 1? Can I say that? Because that means f11 is 0. It is 0. Why? Because 1 is a convex surface. Okay, so the radiation of energy from 1 on 1, I mean on 1, it is 0. There is no fraction of radiation energy falling on 1 from 1. Okay, so f11 is 0. That implies f12 becomes 1. Okay, now we have to find f21. So reciprocity theorem is a1 f12 is equal to a2 f21. f12 is 1. That implies f21 is equal to a1 by a2. Okay, a1 is 4 pi r1 square, a2 is 4 pi r2 square, surface area of sphere, you know that, solid sphere. Okay, that becomes r1 by r2 whole square. Put the values, you'll get the answer as 4 by 9. So the option is B. Let's move on to the next question. Two infinite parallel plates are placed at a certain distance apart, and infinite radiation shield is inserted between the plates without touching any of them to reduce heat exchange between the plates. Okay, this is the important line. Assume that the emissivities of plates and radiation shield are equal. The ratio of the net heat exchange between the plates with and without the shield is. You must have encountered these type of questions. So, and you must be knowing that Q with shield upon Q without shield is equal to 1 upon n plus 1. And what is n? N is the number of radiation shields that you have inserted between the two infinite parallel plates, which in this case is equal to 1. And this formula is only applicable when emissivity of plate is equal to emissivity of radiation shield. This is the important condition. Star star. Okay, so the answer will be 1 by 2. Okay, what happens if the emissivity of plate was not equal to emissivity of radiation shield? In that case, you would have to find Q with shield and without shield. So Q without shield will be, this is 1, this is 2, this will be Q without shield, okay, not writing it completely, sigma, let this be T1, let this be T2, T14 minus T2 raised to the power 4 upon 1 by epsilon 1 plus 1 by epsilon 2 minus 1. Okay, Q without shield. This is Q without shield. And when I will be inserting this shield 3 here, then Q with shield becomes sigma T1 by 4 minus T2 by 4 upon 1 by epsilon 1 plus 1 by epsilon 3 minus 1 plus 1 by epsilon 3 plus 1 by epsilon 2 minus 1. I urge you to remember these formulas. Then you have to take the ratio of them. This will get cancelled out, this will get cancelled out, this will get cancelled out, and you will get the corresponding answer. Okay, so this formula has been derived from these two equations only. So if emissivity of plate and emissivity of radiation shield are equal, you can apply this formula directly. Next question. The total emissive power of a surface is 500 watt per meter square. Power is given in watt per meter square. Okay, so this will be Q by A or E by A. At a temperature T1 and 1200 watt per meter square at a temperature T2. Temperatures are in Kelvin. Assuming the emissivity of the surface to be constant, emissivity is constant. The ratio of the temperatures T1 by T2 is very simple and a very basic question. This is equal to sigma epsilon A T raised to power 4 emissive power. Okay, we have been given E by A, that implies E by A is equal to sigma epsilon T raised to the power 4. Epsilon is constant, sigma is constant, so E by A1 is equal to, or I can say it becomes directly proportional to T raised to the power 4, or you can write that implies E by A for 1 is equal to constant T raised to the power 4. Okay, what you do is take the ratio of this and this, let this be 1. Take this ratio 1 by 2, you will get T1 by T2 is equal to 0.803. Answer will be C. Very basic question. Next question is question number 5. A solid sphere of radius r is placed inside a hollow closed hemispherical surface of radius 4r. The shape factor F21 is, okay, F21. So again your mind should go to those two equations, that is the summation rule and the reciprocity theorem. Let's apply the summation rule. It says that F11 plus F12 is equal to 1 and F21 plus F22 is equal to 1. Using this, we can get F12 is equal to 1. Why? Because F11 is 0. It is a convex surface, so the fraction of all the radiation energy will be going to 2 and it will not be falling on 1. So the fraction of radiation energy from 1 on 1 will be 0. Okay, so F21 is equal to 1. What we have to find now is, sorry, F12 will be 1 and we have to find out F21. So A1 F12 is equal to A2 F21. F12 is 1, that implies F21 is equal to A1 by A2. What is A1? A1 is 4 pi R1 square and A2 is 2 pi R2 square plus pi R2 square. Okay, this will be the area of sphere, that is 4 pi R1 square, and this will be area of hemisphere, that is 2 pi R1 R2 square plus the area of this flat surface, that is pi R2 square. Okay, pi gets cancelled out, pi. Okay, R1 is R and R2 is 4R. Put the values here. F21 is equal to 1 by 12. 1 by 12, that is option A. An infinitely long furnace cross section has been given. Consider all surfaces of the furnace to be black. The top and bottom walls are maintained at temperature 927 degrees Celsius. I'll convert it in Kelvin here only, because ultimately you have to use the values in Kelvin. 927 degrees Celsius will be 1200 Kelvin. This will be 1200 Kelvin and T2 is equal to T4, which is 527 degrees Celsius, that is 800 Kelvin. 800 Kelvin. This will also be 800 Kelvin. Okay. The view factor 12 F12 is 0.26. You have to find the net radiation heat loss or gain on side 1 in watt per meter. Watt per meter. Note the units, watt per meter. Okay. Stephen Boltzmann's constant is given as 5.67 × 10⁻⁸ watt per meter square, Kelvin raised to the power 4. Okay, so can I say that Q13 is 0? Q from 1 to 3 is 0? Yes, I can say that, because it is at 1200 Kelvin and this is also at 1200 Kelvin. So Q13 is 0. Next, can I say that Q24 will also be 0? Because surface 2 and surface 4 are at same temperature, so there will be no exchange of heat transfer. Okay, next, very important part, can I say that F12 is equal to F12 is equal to F14? How? By symmetry. Can I say that? Yes, I can. See here that the fraction of radiation energy from 1 to 2 will be same as the fraction of radiation energy from 1 to 4. Why? By symmetry. So F12 is equal to F14, which is 0.26. Okay, what I get is Q net now will be Q12 plus Q14 for surface 1, because Q13 will be 0 because they are at same temperature. And also I can say that Q14 and Q12 will be equal. So by symmetry, yes, by symmetry, so this will be equal to twice of Q12. Okay, which becomes 2 into sigma into A1 F12 T1 T1 raised to the power 4 minus T2 raised to the power 4. All the values you know, this is T1. Okay, this is T1, so you know all the values. Let's find Q net 1. 2 into 0.5 into L. Okay, so here you get L. What you do is take L here and you will get the answer in watt per meter into 0.26 into sigma T1 you know as 1200 raised to the power 4 minus 800 raised to the power 4. Solve this, you'll get the answer as 24530.688 watt per meter. Units, take care of the units. The next question is, consider the radiation heat exchange inside an annulus between two very long concentric cylinders. Two very long concentric cylinders. The radius of the outer cylinder is R0 and that of inner cylinder is Ri. The radiation view factor of the outer cylinder onto itself. Again, you have to find the view factor. Go by those two equations, the summation rule and the reciprocity theorem. Let's draw a rough figure. This is the outer cylinder. This is just a rough figure to give you an idea. Okay, so this is having radius Ri and this is having radius R0. Let this be 1 and let this be surface 2. Okay, so by summation rule we see that f21 plus f22 is equal to 1. Can I say that f22 is 0? This is 0 because all the fraction of radiation energy from 2 will be going to 1, and there will be no fraction of radiation energy that will be going from 2 and falling on 2 again. So f22 is 0, f21 is equal to 1. That implies f21 is equal to 1. I can write this. Now what I have to find? The radiation view factor of the outer cylinder onto itself. You have to find f11. Okay, f11 plus f12 is equal to 1. For finding f11 we need f12. We have found out f21, so a1 f12 is equal to a2 f21. F21 is 1, f12 we will be able to find out now, that is a2 by a1. Okay, that implies a2 is 2 pi RIL upon 2 pi R naught L. This gets cancelled out. Very long concentric cylinder, so f12 is equal to Ri upon R naught. Okay, put this value here. You will get f11 is equal to 1 minus Ri upon R naught. That is option D. Next question is, two large parallel plates having a gap of 10 mm in between them are maintained at temperatures 1000 Kelvin and 400 Kelvin. Given emissivity values epsilon 1, epsilon 2 and Stephen Boltzmann's constant is equal to 5.67 into 10 per minus 8 watt per meter square Kelvin divided by 4. The heat transfer between the plates in kilowatt. Beware of the units, kilowatt per meter square. Okay, again you must be knowing this formula directly. We have encountered this type of problem earlier also. Okay, this b1, this b2. What you know is q net by a is equal to sigma t1 raised to the power 4 minus t2 raised to the power 4 upon 1 by epsilon 1 plus 1 by epsilon 2 minus 1. Put the values. 5.67 into 10 raised to the power minus 8. T1 is 1000 raised to the power 4 minus 400 raised to the power 4 upon 1 by epsilon 1, that is 1 upon 0.5 plus 1 upon 0.25 minus 1. You will get the answer in watt per meter square, which will be equal to 11049.696 watt per meter square. Convert it in kilowatt per meter square, that is 11.049 kilowatt per meter square. Direct formula based question. Remember this formula, it's an important equation. Next question. The emissive power of a black body is P. If its absolute temperature is doubled, the emissive power becomes. Very basic question. You know that emissive power is directly proportional to t raised to the power 4, because however emissive power is equal to sigma epsilon a t raised to the power 4. Okay, sigma is constant, epsilon is constant, a is constant, we can say this. Okay, now the absolute temperature is doubled, so 2 raised to the power 4 t raised to the power 4, this will become 16 times e1 e2 or whatever you can say. You can replace this proportionality sign with is equal to k is equal to k. This will get cancelled out 16 times. The option will be D. Okay, next question. Okay, so the next question is, the peak wavelength of radiation emitted by a black body at a temperature 2000 Kelvin is 1.45 micrometer. This is the peak wavelength. Peak wavelength of emitted radiation changes to 2.90 micrometer, then the temperature in Kelvin of the black body. Very basic question on Wiens displacement law. Displacement law, which states that lambda mt is equal to constant. That implies lambda m1 t1 is equal to lambda m2 t2. Okay, now put the values and get the answer. That implies what we have to find? We have to find t2 lambda m1 t1 upon lambda m2, which is 1.45 into 2000. Do not worry about the units of micrometer because this is in micrometer, this is in micrometer, it will get cancelled out. This is in Kelvin, you will get the answer in Kelvin. 2.9. That implies T2 is equal to, what will be T2? T2 will be 1000 Kelvin. Answer